everyone. Thank you for joining our weekly Kent Seminar series. And today we are honored to have Professor Konstantin Samaras. So we'll give a brief introduction. Professor Samaras is an associate professor from Carnegie Mellon University's Department of Civil and Environmental Engineering. He is also a fellow at the Wilton E. Scott Institute for Energy Innovation and is also the director of the Center for Engineering and Resilience for Climate Adaptation. Professor Samaras is also an adjunct senior researcher at RAND Corporation. His research spans energy, climate change, automation, and defense analysis. Professor Samaras received a joint doctoral degree in civil and environmental engineering and public policy from Carnegie Mellon University. He holds master in public policy from New York University and bachelor's in civil engineering from Bucknell University. And before we proceed, I would like to invite Professor Aleftia Kuntu to complement these introductions. Professor Kuntu, please.
Sure. We are very excited to have Professor Kostas Samaras with us today and hear more about his exciting research on assessing pathways for U.S. passenger vehicles and last mile delivery decarbonization. Without further ado, Professor Samaras.
Just a quick reminder for everyone. Professor Samaras will have 40 minutes of presentation and conjugate with 20 minutes of Q&A. If you have question, you can go to the participant buttons. There is a raise hand option there. You could raise your hand and ask the question directly, or you can type your question in the chat box and I will happy to ask them on your behalf. And please, Professor Samaras, you can start sharing your screen. I will stop sharing my screen.
Thank you so much, Denisa, and thank you so much, Professor Kuntu, for this invitation to be here amongst this distinguished group of Kent Seminar Series lecturers. I'm very honored to be here and to be speaking with the wonderful faculty and staff and students of UIUC. It's truly an honor. So today we have 40 minutes. And I'm going to make sure that we have plenty of time for questions, and I want to get through a bunch of topics because I want your feedback. We're going to talk about our work on transportation decarbonization and work that's been published. We're also going to talk about work that is very much in progress at the end of this. So I want to get your feedback on how things are going and what we can do better. All right, now, none of this would be possible without the amazing work of our graduate and undergraduate students that I get to work with, as well as our faculty collaborators. I work in two main areas. One is understanding the transition to a decarbonized economy in both the transportation and electric sector, and have a really great group of students that work on that I get to work with that. And then a second focus area that I'm not talking about today is climate resilience and climate resilience for infrastructure. That is a super important topic, and I know it's important to the faculty and students at UIUC, and would happy to be connected to folks offline about our work in that space. All right, now we remember transportation has evolved before, and it started with in the recent history. It started at the turn of the 20th century with horsepower, and with horsepower came horse manure. And if you look around Chicago or New York or Boston, Philadelphia, Pittsburgh, DC, you will see boot scrapers, basically pollution control devices, removing horse manure from your shoes, built into the built environment. And so we traded this for engines that puffed, leaded carbon dioxide laden gas, and we solved one problem and introduced a much bigger problem. And we, as civil and environmental engineers, really have to grapple with our legacy of racism and infrastructure. And so this is what we replaced horse and buggies with, is highways that cut through neighborhoods, highways that disproportionately affected communities of color. And we live with this legacy today. And in this transition, you have to, as students, ensure that the next transition does not look like this one. Transportation is a problem in greenhouse gas emissions. It's now our biggest problem. It's the largest source of greenhouse gas emissions in the United States. The thing that is important that many of you know, but I don't think the general public grasps this yet, is that carbon dioxide emissions are essentially permanent. When a smokestack that is generating coal power turns off, the sulfur dioxide that was emitted from that smokestack starts to fall out of the atmosphere, in a relatively short amount of time. The carbon dioxide that was generated from that coal power plant, that's not the air pollutants that we would be breathing in and causing respiratory distress, like sulfur dioxide and particulate matter. Carbon dioxide as a greenhouse gas stays in the atmosphere for hundreds to thousands of years or longer. And so from our time scales, that's permanent. We should have started earlier to decarbonize, we didn't. So now we have to do a lot of work quickly. In transportation, our work looks like this. These are US greenhouse gas emissions from the transportation sector over time. Light blue here are cars. Red is planes, orange is trucks, and then ships and other are up top. What this means is we can't solve climate change without dealing with transportation, and we can't solve transportation without dealing with cars. If we were to meet an 80% below 2005 transportation emission standard, that's that dashed line there, all of this activity has to fit underneath that dashed line. Now, 80% below 2005 is not enough. It has to be down to zero. So we have to figure out how to decarbonize all of this activity. Well, we have three things that we can do: change the technology and the vehicle efficiency, change the carbon intensity of the fuels, or change our total distance traveled, or some combination of these. Now, we've been working on vehicle electrification for a long time, and typically we'll get the response from a general audience, well, what about coal, right? So yes, coal exists. And if we are charging with 900 grams of CO2 per kilowatt hour electricity, that's a kind of a modern coal plant, we are still better than a car that gets 25 miles per gallon. Now, we're not charging with 900 grams per CO2, 900 grams of CO2 per kilowatt hour electricity anymore. The current US average grid is closer to 400, and better in some places, worse in other places. We'll talk about that. But there's more than carbon dioxide that causes damages from energy use. These are the operating cost of a gasoline vehicle and electric vehicle, and this is specific to Los Angeles. And there was a paper from my colleagues at Carnegie Mellon led by student Matt Bouchon, it just came out, that estimated some damages from air pollutants in different parts, used a different model to estimate damages from air pollutants in different parts of the country. This is in Los Angeles. And so running a vehicle, operating a vehicle in Los Angeles will cost you this much in green for a gasoline versus electric, and then this much in orange for the air pollution damages, and then this much in blue for a $50 per ton carbon tax. So you see that electric vehicles are already cheaper than gas cars, and they're definitely cheaper when we start adding in the external damages from pollution. But pollution and CO2 are not the only damages that are caused by vehicles. This is the Cybertruck running over a bollard there, a little a traffic sign. That sign about the size of a small person, right? So you know there are traffic and congestion and safety externalities that we need to worry about in the transition to decarbonize transportation that have nothing to do with electricity. So even if we had an electric vehicle charged on all renewable or low zero carbon electricity, we still have the big social damages of congestion, crashes, and noise that are generated from driving vehicles. So we have to think about reducing these and getting these to zero at the same time we're reducing our environmental externalities down to zero. There are lots of new technologies on the horizon that potentially could help with crashes and congestion, namely the automation of vehicles, as well as the shift to micromobility and advanced public transit. Automated vehicles are not for sale yet. This is Carnegie Mellon's automated vehicle from many years ago, and it does things that you would imagine that you'd see on videos for automated vehicles at UIUC or other places. You program it to where you want to go, and it goes where you want to go. And a vehicle like this, it actually can cross the country with relative safety, as long as there's a person completely alert, ready to smash that big red button when something goes wrong. So these vehicles are not yet for sale, but are they going to be for sale this year? No. Next year, probably not. But maybe through the end of the decade, maybe the beginning of the following decade, we'll see how things go. Eventually, these are going to start affecting energy use in a couple different ways, which we'll talk about. Now, just for safety's sake, if you have a Tesla, that's great. You do not own an automated vehicle, not at all. You have a partially automated vehicle, level 2 automated vehicle, and please do not do this, because the vehicles that are for sale for right now require your full attention the entire time that you're driving them. Thank you. But what they do enable is collision frequency and severity reductions with different technologies: lane departure warning with active lane keeping, crash avoidance with active braking, and dead spot monitoring and with active avoidance. So we have Professor Corey Harper at Carnegie Mellon and us and others have published on how these early automated features can help save energy uses associated with crashes. Now, if you're going to go buy a vehicle, buy the cleanest you can, buy electric if you can, and please buy the safety package, because this is really instrumental in starting to bend the crash curve in vehicle driving. Now, we have a whole bunch of work that's ongoing in this area. I'm going to just give the titles of what's happening and mention and show a couple of the students that have been working on this. But these are some of the factors that go into how we model the energy and environmental implications of a future transportation fleet. So how do people use these vehicles? How do they affect energy use? Are they going to be high density urban pods, or are you going to travel from UIUC to Chicago, watching Netflix, or even better, traveling from UIUC to Indianapolis or Pittsburgh, kind of sleeping, right? These are different travel modes. They might extend the commute range if people are, not having to drive, or they might enable kind of dense urban shareable networks. Will these cars be owned or will they be shared? Also super important. And how will they affect equity? Will automated vehicles enable additional transit service through shuttles or purpose shared automated vehicles to communities, and this happens to be Pittsburgh, communities around cities that don't have as dense of a network of transit as the urban core does. These are all things that our students are investigating. And when you look at this, it's like, okay, vehicle efficiency of technology could get better, right, as we electrify and as we automate. We and others have done papers on how early automation is going to improve the fuel economy of driving. But some of our colleagues have done papers on how automation might increase the total amount of energy use per mile if the sensors, the cameras, and the computing equipment start to erode the driving range of a traditional electric vehicle. Now, the carbon intensity of the fuels, here we're talking just about electrification, so we're hoping that continues to go down, and we expect that it will. But the real big wild card here is the total vehicle miles traveled. How will automated vehicles affect total vehicle miles traveled in communities around the country and around the world? And really, we do not have an idea with this. We don't have a great sense of what this is going to look like. We can model it, but we won't know until this actually starts to roll out. So there's all this uncertainty around the future passenger transportation system that we would need to model, that one would need to model in order to make some understanding and policy pronouncements about where we should go and what we should do next. We incorporate these and others into a robust decision model. Now, robust decision making is methods that came out of the RAND Corporation and some of our mentors there. This slide is from Dr. Jordan Fischbach there, but I like it because it tells us the difference between what we normally do, which is try to imagine a couple scenarios, and then under those scenarios, what are the policies and infrastructure that will get us to be successful under those specific scenarios. So that's a predict and act approach. And that we don't think is good enough for something that is subject to such deep uncertainty like the future of transportation, because of all the factors that we've been talking about. And so what a robust decision-making process does is basically model every proposed strategy and identify the vulnerabilities of that strategy. That strategy might be requiring electric vehicles by a certain date. That strategy might be subsidizing automated vehicles in the dense urban core. Strategy might be some high pollution externality on fuels. Then we're identifying how well those strategies get us towards some threshold. In this case, our threshold is transportation decarbonization, either 100%, 90%, or 80%. And then we can look to see where those strategies cluster around success thresholds, or where there are multiple points of failure, so that we can discard individual strategies and cases. And so what an RDM process does is model every possible proposed policy and strategy under the broadest possible range of plausible futures in an internally consistent way, so that you find clusters of success and you identify robust policies. Let me talk a little bit about what that means, and we'll get to some results. So in this first piece that we've done, our goal, our threshold here is to reduce CO2 from the light duty vehicle sector by between 80 and 100%. And that means that we have a CO2 threshold in 2050 of 250 million metric tons. So that's the goal in 2050 that we're trying to get to. Now, this is just the 2050 number. In this first paper, we were doing it kind of annual through 2050. In the work that we have ongoing, we're looking at an entire carbon budget. And so there's a difference in strategy when you're trying to be 80% or 90% below a target in 2050 versus spending down an entire carbon budget. So I'm going to talk just about the annual number here. So here, pretty simple schematic of the modeling system. So we're building an open model of the transportation, energy, and greenhouse gas emissions for light duty vehicles in the United States. There are several that are out there. Ours is going to be a robust decision model that incorporates uncertainty from a lot of these new factors that we've talked about. So basically, how many cars, how far they go, what are they charged on, and how fast do new vehicles enter the fleet, and how fast do old ones exit. The thing that is important here is that there are a whole bunch of correlated factors that we need to make sure that we're developing internally consistent pathways. So you probably are not going to have a sample year where total vehicle sales are really, really high, but the economy is in a recession, or total vehicle mile travel growth is really high when the economy is in recession, right? And so we have to think about adjusting the scenarios to make sure that the signs are at least aligned. And then we're modeling across the broad range of future improvements on AV adoption, year of AV market introduction, EV adoption, EV policy and sales restrictions, and the way that the grid changes. So we're trying to model all of the different ways that might affect our outcome, which is CO2 in the transportation sector by 2050. So here is the kind of the base case that we can talk through. On our x-axis is light duty vehicle CO2 in million metric tons. Remember that 250, anything over 250 is not a feasible solution in our estimation, is that we need to be 250 or below. So that 250 million metric tons represents an 80% carbon reduction target, and about 110 represents a 90% carbon reduction target. And on the y-axis, we have electricity carbon intensity. So how much CO2 is in our electricity? On average right now in the United States, we're between 380 and 400, which is above the axes of these graphs, right? So we're not going to make it there until we get down to 200 or less. We really need to be getting down to zero. So what a graph like this shows us is first the possibility space under a static travel condition. And this means that, okay, any point in this shaded region is going to meet our 80% carbon reduction target, and any point in this region is going to meet our 90% carbon reduction target. And what that means is, for a 90% carbon reduction target in light duty transportation, we need to have at 0 carbon electricity, we need to have 84% electric miles in 2050. And we're going from close to 0 electric miles now, a couple percent. And as the electric sector moves away from 0, so maybe we do a really good job in decarbonization, but we get it instead of down to 0, which 0 is a very low number, as our colleagues would say. Now it's at 100. So 100 grams of CO2 per kilowatt hour is great. It's not 0 though. So now at 100, we're going to need more than 90% electrified miles, right? And as we move all the way up to 200, now it's basically we're going to need very close to 100% electrified miles. Now this was under traditional projections of how far we travel. And so this is where the automation piece starts to come into play. So the way that automation comes into our analysis is, number one, how far we travel. And number two, underlying all this is how it affects the efficiency of vehicles. So here is how far we travel. Now, you all are in transportation, and you'll be very familiar with VMT trends, vehicle mile travels trends, or vehicle distance traveled trends in the United States and around the world. And we travel a lot. We travel 3,000 billion miles in transportation annually in the United States, 3 trillion miles. And what if automation starts to open up travel possibilities and induce additional demand that we haven't even thought about yet? And we do not put any policies in place to encourage dense development, as well as ride sharing or vehicle miles traveled fees, other ways that we might discourage the use of additional driving. If we don't do that, and we go from 3,000 billion miles to 4,000 billion miles or 5,000 billion miles, as you travel this way in total VMT per year, the amount of electric vehicles you need to still meet your target really goes up to 100 very fast. And that's also assuming that our electricity sector is decarbonizing separately, right? So under 0 carbon electricity sector, which is where we need to be, under a traditional model of travel, we're going to need, as I mentioned, 84% EV miles in the system. As we go to 4,000, even under 0 carbon, now we're going to need more, right? So because there's still going to be additional travel, there's still going to be some gasoline vehicles and others that are traveling around, and some of the AVs may or may not all be electric only, right? So this is a piece of uncertainty that a lot of people don't kind of put into their models, which is there may be plug-in hybrid or even pure gasoline automated vehicles, unless there's policies to encourage electric only. So as we travel more, we'll need more electric vehicles, and we'll need more electric decarbonization. But as we potentially travel less, right, you need fewer. So the equation goes both ways, that reductions in travel reduce the amount of total EV miles you need in the fleet, all right, to meet some specific 90% target. Now, what about changing load factors and encouraging sharing? Stuff that we definitely should be doing. So here's our current load factor, kind of 1.6 something in the number of people per trip, and if we're able to move that load factor, above 2 towards 2.5, now all of a sudden we're able to approach our CO2 targets by having fewer amounts of EVs. That's good, and we should be doing that. But the thing that really struck me about our results here is, if you're able to get to 100% EVs with very, very low CO2, you're basically doubling or tripling the benefit of additional sharing. So we need to do all this. We need to have sharing, but really, it makes intuitive sense. A largely decarbonized electric sector running most, if not all, EVs will have a big CO2 reduction relative to the status quo. Now here, it's like, let's think about what our travel budget frontier could look like for enabling a very, very low passenger transport sector in terms of carbon emissions. So I mentioned that we do 3,000 billion miles. 2/3 of our VMT are in urbanized areas. Now, UIUC is probably an urbanized area. Outside of Pittsburgh is probably an urbanized area. There are urbanized areas, according to DOT, that may or may not look what you would think about as an urbanized area, but they're within an urbanized region. But still, if 2/3 of our VMT is within urbanized areas, we have opportunities to make considerable reductions through active transportation, public transportation, and micromobility. Now, this is the scale that we're dealing with here. To jump from 3,000 down to 2,200 or thereabout, this is all of the urban vehicle miles traveled in the 10 most populous states. And so there is a bench of VMT that can be reduced in these areas that reduces the total number of EVs that we would need in the fleet in order to meet our decarbonization goals. So fewer VMT, fewer total number of EVs needed. More VMT, we need more EVs in the fleet in order to meet decarbonization goals. Now, the problem is EVs and vehicles themselves are not phones. We don't throw these away every few years. People sell them, but then they enter the secondary market and are driven for many, many years. The average age of the vehicle is 12 to 15 years. And the tail of these vehicles, the distribution of the tails of these vehicles can go into the 20 and even up to 30 years. And so we modeled a range of how the fleet would evolve given sales, given exits, given fleet age, and also now not shown here, some work around what COVID did to auto sales. And we said, hey, if we wanted 100% electric vehicles in the United States, we would have to sell only electric vehicles starting in the year 2020, which is going to be impressive because we get a time machine and go back there and require that and then start selling only EVs. So we will not age out the current gasoline fleet by 2050 without some additional policy. There will be a vehicle that's sold in 2021 has a decent chance of being on the road in 2041, maybe even 2050. However, we could still meet our kind of bounds of decarbonization, kind of in the lower bound of 40% electric to upper bound of kind of 60 to 80% electric, even if we did limited policy and waited until the early 2030s to require only EVs. But really, we see a lot of policies now about, we're going to start selling only EVs in 2035 or 2040. That is the absolute latest that you can start this and still have some semblance of natural market evolution of the fleet and turnover to get to a 2050 target. So I mentioned our robust decision-making work. This piece is not yet in a paper, but these are modeling all the single policies. And there's 2,000 cases here, and we're doing other runs with more thousands of runs. And so orange here is bad. So orange is, this was a case that ran through the policy. It looked to see if we met a threshold. It did not, and orange is not going to work. That's some sort of policy around electricity being too low, or in terms of the pace and scale of decarbonization, or electric vehicles starting too late in terms of the acceleration of sales. Then you have the blue dots, which are, these are the cases that worked, but they were at risk of failing because of they're kind of on the line. And then there are the green dots, a much smaller subset here, that policies that are pursued under these green clusters have a much higher likelihood of achieving our objective. And here the case is decarbonization in the transportation sector. Happy to talk about this. This paper is kind of in progress now, but I wanted to show here that intuitively more cases work when you have very, very low electricity and you start to sell electric vehicles early in this timeline between now and 2050. Now remember, active transportation and public transportation are a hedge against this uncertainty. And so as we shift solo vehicle miles to other modes and also decarbonize those modes, we are hedging against some of this risk of not meeting our targets. We know that different parts of the country have different VMT and population. California cannot do this all themselves. We're going to have to make sure that this is a nationwide strategy of decarbonization and electric vehicle and public transit and active transportation rollout. We also know that electricity is not a single grid across the United States, as we keep the folks in Texas in our hearts and minds after what they've suffered through this last month. But electric sector decarbonization continues apace across all regions, even the Midwest, where it had been traditionally coal heavy. And as we continue to track that, we do this on our research website, emissionsindex.org, where you can take a look at how the carbon intensity of the power sector is changing, and all the code and data is there. What we didn't talk about here is the life cycle emissions, which we work a lot in. So making batteries, making vehicles, making fuels, all this creates emissions. This requires the concurrent decarbonization of the electric sector, as well as the industrial sector, so that we have the lowest possible carbon material inputs to a pulse of 50 to 200 million electric vehicles just in the United States that we would need by 2050. Now, this paper basically said, hey, you want to decarbonize, you have to get your electric sector close to zero, and you have to have most electric miles by the middle of the century, kind of 60 to 84% as kind of the minimum targets here. This requires a lot of EVs. It also requires lots of public transportation and lots of active transportation in order to make this work. And lots, I mean, like more than you ever would have imagined that you would need is what we need. And we're going to do it. We have a pathway. It's going to happen. It's the challenge is now is kind of taking action that is consistent with this scale of the challenge. I'll mention that our previous Cash for Clunkers program bought back 700,000 cars and cost $3 billion. If we only sold EVs starting in 2021, in 2030, there'd still be 100 million gasoline vehicles on the road. If you wanted to buy all those back, it would be $500 to $600 billion. And if we didn't do that, those vehicles would likely be on the road, for a decade or more after that. So electrify everything, clean the grid, and move more while driving less. This paper was published in Environmental Research Letters. You can scan the QR code and get it. It was led by PhD student Abdullah Alarfarj, and Professor Michael Griffin was another author. I want to move now to this second piece because I know we're getting towards the end here, but this is the in-progress work. The pandemic has affected the way that people get stuff, but even before the pandemic, there was 1.5 million packages being delivered in New York City alone every day. We said, hey, you know what? Let's go figure this out. If people are going to deliver stuff by drones, let's go get the energy use. And we and others had published papers about kind of simulating energy use in drones. We were more interested in let's go build a drone, right? So here's a little hover test. Drones, take off. Make sure that the propellers work well. We put a sensor box on it. The students 3D printed a box. We put an anemometer on here, and a whole bunch of students and faculty work on this project. The project that I lead, Department of Energy funded, on understanding the future of delivery with different types of robots. And I'm very grateful for all the students that have been working on this and our colleagues in the Robotics Institute. So we built a drone. We then started doing some first principles energy models of drones. These are small quadcopter drones. Unlike the helicopter industry, there's not a robust industry for doing kind of CFD and first principles analysis on drones. We kind of started that a little bit and try to think about how do we model the energy use of this and compare it to the sensors that we're going to put on here. We put this stuff together. You see a little package underneath there. It's about 0.5 kilogram, and we flew 200 plus sorties with at different speeds and altitudes, ranges, and on a fixed course outside of Pittsburgh, and collected a whole bunch of high resolution data on what happens when you fly a package with a drone. And so the data that we collected is power and altitude and speed and time and wind measurements, position, a whole bunch of pretty high resolution information that we're now sorting through and figuring out what to do with. We have a data set that is public already. It's published on Figshare, and we have a bunch of papers that are in the works on kind of assessing what all this means for transportation and for decarbonization. The thing that our student one of the students who led this, Thiago Rodriguez, came up with if you look at all the sorties, you have the quadcopter goes up, it flies for a while, and then it goes down. And there's different forces and energy requirements that are happening in these three regimes: the takeoff, the cruise, and the landing. What Thiago developed was a machine learning algorithm to identify these portions of all the flights, so that we can run all the flights through this algorithm and say, all right, this is a takeoff, this is a cruise, this is a landing. And we can start to model across all of our flights the impact of weight, the impact of distance, the impact of speed. And so, as one would imagine, a heavier package and a heavier drone are going to require us to have more energy use. This is watt hours per package, and this is a two-way delivery distance. So if it's 4 kilometers out, 4 kilometers back, except when you're going out, you use more energy when then you're coming back because you've dropped off the package. So obviously, weight of package is part of this, but speed, right, is really important. So a slow drone uses more energy because it spends more time in the air, and so this is relevant for urban policy, because you might not want drones at all. You might want some drones, but you don't want them to go too fast. It might be noisy, but as you think about optimizing drone delivery policy, we're trying to think about making sure it's safe, that it's equitable, and it has the lowest possible environmental footprint. And a slower drone is going to use more energy because of more time in the air. So these are the difference in payload across cruise speed. And so this is the graph of a slow drone versus a fast drone, and the uncertainty is how heavy the package is. It's interesting is that with a slower drone, you basically top out with a battery. You can't get it to go that far because you use up all the battery's energy. Now, we did a Monte Carlo assessment to understand the difference of drones between other last mile delivery services, truck, bike, van, etc. And on a megajoule per kilometer basis, yes, a small plastic drone uses less megajoules than a several ton steel truck. But you have to think about getting this to a per package volume. So this is where the uncertainty analysis really is important, is because there's all kinds of assumptions that we can embed in here about the volume of the cargo space, the delivery route, the types of packages, the weights of packages. But still, this is in progress, hasn't been reviewed yet, and there's other work that's similar that's out there that kind of agrees with this, is quadcopter drones and electric vans and e-cargo bikes live towards the bottom of this energy use per package pyramid here. And the more of packages that we can get out of diesel vans and into electric and non-motorized or limited motorized modes, the better that we'll have on a total megajoule per package basis. Now, you're not going to be able to deliver pet food with a drone. These are small packages, high value items, iPhones, microphones, USB sticks, things we might need for our Zoom life right now. Now we can do the same thing with greenhouse gases on a per package basis. And you see that quadcopter drones still are competitive with some of the more kind of e-friendly modes. You'll see medium duty e-truck here. If we can get an electric truck or an electric van packed with packages, that's going to be one of our most efficient modes to get stuff on the last mile. Now, why this is important is that this is from Amazon's patent filing of a floating warehouse where they can potentially send a package down to you in a glider drone. Many of the package delivery companies are experimenting with drones to increase the amount of packages they can deliver within a time frame to get them out really fast, as well as potentially in rural areas to increase the efficiency of having to drive a diesel truck from house to house to house. So the drones are not going to replace a large portion of freight, but there are opportunities that they replace some, and we're trying to investigate what the total energy and greenhouse gas emissions are from those. Now, we also have in the works, sidewalk robots. I know this is a little bit loud. This is our sidewalk robot rolling around Carnegie Mellon's campus. Both the drone and our sidewalk robot are autonomous, and we want to make sure that we're able to measure the energy of both the vehicle and the autonomous brain itself. And we're doing that with this robot. There's the data that we have here is just about to be published. It's not ready for analysis yet, but I'm happy to come back and talk about this work as we move forward here. So what are some robust policies for decarbonization, right? There's wide uncertainty, but there are synergies between electrification, automation, and travel reduction. Shared rides and early electrification are really important, and they open up options for later. But really, travel reduction is a no regrets policy that allows decarbonization to continue amidst the rest of some of this uncertainty. And as we've seen now, drones can potentially reduce energy and greenhouse gas emissions per package on some routes, but there's going to be other social equity and environmental concerns around automated delivery that we and others are experimenting with. And I will say, on the drone side, we're pretty excited about some relationships that we're finding between energy and package delivery and the characteristics of drones. I was debating whether to put it on this slideshow yet or not. I wanted to kind of marinate a little bit more to make sure that we're doing it right. But we think that there's a generalizable relationship that we can potentially use across different types of and sizes of drones. I'll report back on that and tell you how that's going. So that's my 40 minutes. I want to make sure that there's enough time for questions. I know I kind of did a little bit broad of two different papers, but I can dive deeper into any of these or talk about any of the work that we've been doing in transportation decarbonization. I'm so grateful for all of your attendance today. I know being on Zoom is hard. Thank you so much, and looking forward to connecting either now or later on in the day.
Thank you so much, Professor Samaras. It's a very interesting presentation. So I think we have Professor House for a question. Professor, you can unmute yourself.
Yeah, thank you. And thanks, Costa, for a great presentation. This was really exciting work and really interesting to me. I'm curious about the work that you guys have done with regard to drones. I guess I'm a huge nerd for looking at what FAA is doing and kind of air travel in general. So I'm curious, I imagine there's going to be a lot of restrictions as to where and how drones can fly. Have you guys considered, when you're doing the analysis in terms of the carbon footprint and other impacts of drones, that they may be taking very suboptimal routes to go from one point to another? And I did see some large error bars, so I didn't know if that was a part of what you guys are seeing.
Thank you, Professor. This is an area that we've been really diving into, and we have some work that's starting to get published in robotic conferences, and then it's going to make our way to the engineering journal papers. Our team has been looking at how route and wind affect drone delivery itself. You have a small vehicle, and the wind itself is going to affect the energy use and the route that one chooses. So we have been experimenting with and playing around with kind of trying to come up with prediction algorithms that say, here's the potential wind for this route, and here are the other hazards along this route. This route goes over a school, this route doesn't. This route is only over a road, this route doesn't. And so there's an optimization that one would need to do primarily first for safety, and then secondarily for energy. And those are the types of kind of processes that we're going through now. I will say that FAA seems to be loosening restrictions rather than tightening. So right now you can't fly a drone at night. There's been a notice for public comment that can be lifted. And so we have investigated all of the causes that would cause all of the reasons that would cause a drone to not be able to fly. Weather is the main one, temperature, wind, and visibility. And so we can scan the aviation weather to look at that. And night is obviously the biggest one. As soon as they lift that, if they do lift that, that opens up another avenue of operations. But really, there's lots of super neat work to think about how to plan what would imagine to be a transportation system, a vertical transportation system in profile that minimizes energy, maximizes equity, minimizes noise, minimizes a lot of the things that were not considered when we designed the transportation highway system can be done now in the air mobility system.
Great, yeah, thanks, and look forward to discussing with you more this afternoon.
Great. I believe we have Professor Kontu.
Sure. Thank you, Professor Samaras, for the very interesting presentation, and particularly for highlighting the role of electrification and vehicle miles traveled reduction on meeting carbon reduction goals that are very important for the transportation sector. So my question is mostly related to the feasibility of achieving these goals, given that, for example, shifting to different modes, right, or vehicle miles travel reduction could be more doable in urban environments versus rural, since certain investments for infrastructure would take years to materialize, particularly regarding building capacity for transit or enabling rural populations to travel less, given that they need still to access various opportunities. So have you done any work on that front? Is that something that you are interested in looking into?
Thank you, Professor. And I would always be up for collaborating with you or the great faculty and students at UIUC on these really important issues. The type of work that we've been doing here are trying to identify the pathways for infrastructure, like how much public transit do we need? How much biking do we need? How much EVs do we need? And once we kind of identify those, then the next is like operationalizing that plan. Really, the carbon math here is daunting. And this is why I kind of make the point in the presentation that we're going to need more than anybody imagines. And so they're really like the scale of how much we will need to in public transit, both in increasing urban miles that move to transit as well as rural miles is large. So I have optimism, but I'm very clear-eyed on the scale of the challenge. Like shifting 3 trillion vehicle miles in any reasonable time frame is going to be a giant lift. Luckily, we have the great students of UIUC and others to help us make that happen.
Thank you. And I have one additional question, if you don't mind. It seems to me that you highlighted the importance of doing this transition in an equitable manner. What would this take? What would be, so for our students, what would they need to start? What are the indices that they need to start looking into in order to propose solutions that are equitable and account for how different population segments would have access to electrified mobility or other mode opportunities?
I think it's recognizing that the role of the engineer is not just the optimal alignment. The role of the engineer is the best alignment possible given the other objectives that one has to optimize around. And equity, community, and environment are very much intertwined with what the optimal alignment looks like. And it's important that practicing engineers and engineering researchers are designing policies that don't disproportionately burden historically burdened communities or historically vulnerable communities. And there are some tools that we and others use. There's one from the EPA called EJ Screen. There's tools from the Department of Energy. There's tools from California. And at least at the very minimal level, it's like here are vulnerable communities. Here are existing negative infrastructure elements. How do we design the system, understanding that context in place? And really at the heart of this is ensuring mobility and access for everyone. The transportation is about mobility and access. And a lot of times, we are now, if I can allow me to pontificate for 20 more seconds, several decades past the passing of the Americans with Disability Act, and many of our public transit systems are not fully accessible. And we look at our sidewalks and our other transportation systems. We don't have accessible transit. We have disparate amounts of frequency in underserved neighborhoods, and so engineers have a professional and ethical responsibility to be to incorporate equity into their designs. And I'm confident that the students at UIUC will be able to do that.
Thank you.
Great. So I believe we have one question from Marcela Maria in the chat box. She asked, what is your opinion about the decarbonization process in the execution of asphalt pavement?
Okay, so I defer to the great pavement experts at UIUC on this. So this is if you all remember, you may not remember, thankfully, there was a time a few years ago where there was, people who were not working in energy got excited about solar roadways. Does anybody remember solar roadways, right? And like, this was an idea where somebody was going to make a solar panel that was going to be on the road that we were going to drive over the solar panel. And, we love solar panels, but we thought putting a computer on the road was a bad idea. And the reason is asphalt is rocks plus trash from a refinery, right? So asphalt is the bottom dregs of oil refining, and basically nearly given away and mixed with rocks to create a roadway surface. Plus, if you're going to have solar, it'd be better to put it next to the road or on a building or literally anywhere else than on the road, where number one, you would drive over it and break it, but number two, you have to compete with rocks plus trash. And the decarbonization process of asphalt, is going to involve the upstream. So are we going to be able to make low carbon asphalt? Are we going to have carbon capture and sequestration at the refinery? Absolutely, that's required to get the CO2 down. But really, what I'm more excited about is high albedo pavements, and can we make flexible pavements that reflect more of the sun's energy than asphalt that absorb all that energy and make our communities really, really hot. So I defer to you about the latest technologies in asphalt decarbonization, but I do know that very, very dark pavement in urban context increases the heat island effect, as you all know, and it would be great to find low cost, low carbon alternatives to that, and soon, because that is something that actually could get rolled out fast. If you think about, asphalt repaving happens every few years, right? Concrete repaving, a little bit longer than that, but asphalt repaving and resurfacing could be every few years. So if you all can invent some magic, very light asphalt that can go down quick and be resistant to snow and have the performance of asphalt, you would be doing a great service for humanity.
Thank you, Prof. And we have the next question from Angeli. You can unmute yourself.
Hello, Professor Samaras, and thank you for the nice presentation. If I may piggyback on Professor Contu's questions and the mindset of being a devil's advocate, say we have reached full deployment of small and large electric vehicles. I'm curious, what are your opinion and sorts of questions and concerns that you have once we get to that stage? Even remembering what you mentioned, that initial innovations don't really push to get negative impacts. But say we get there, what's your concerns now for later?
Well, the thing that we need to recognize with electrification under the current battery chemistries, that there are real problems, environmental and social problems in the battery supply chain. Critical materials and conflict minerals from all over the world. As electrification ramps up, we imagine that finding batteries that are and having battery supply chains that are ethically sourced is really, really important. If we were to get to full electrification here in the United States or elsewhere, there's still cars, right? And so cars still cause crashes. If they're automated and connected, maybe the congestion would be lower a little bit. Maybe the crashes hopefully will be lower a little bit. But in the end, it's still a vehicle. And how do we make sure that everybody has access? Number one, if these are expensive, that's going to be a challenge. But number two, how do we ensure that quality of life for people in urban and rural environments is enhanced, not degraded. And some of that might be by designing infrastructure that allows people to interact more rather than sitting, for many, many hours in the car commuting.
So, yep, I believe Professor have another question.
Just wanted to add one quick comment. I wish the asphalt binder was free. It's usually about, it's right now about $500 a ton, sometimes up to 600. So it is, I mean, which doesn't sound so expensive compared to petroleum, but it is quite pricey. So just wanted to clarify that it's still quite pricey, and so we're not just using it because we're getting a good deal or getting it dumped on us. And there are a lot of wastes we're trying to incorporate right now into the pavement. Things like waste plastics, things that would be free. Of course, asphalt is highly recycled as well, so we're using a lot of recycled product these days. But just wanted to add that.
I appreciate it.
Yeah.
And maybe if you can help, shed some light on this. The asphalt that is purchased, is it mostly when agencies are making asphalt versus concrete decisions, they're doing it on a life cycle cost basis. And is the low cost of asphalt the driving factor of why they wouldn't do concrete? So concrete has a much better albedo.
Actually, it's one of the reasons. One of the bigger reasons is a community issue related to noise. Asphalt pavements usually have quite a bit less noise than concrete pavements. So definitely one of the biggest issues is noise pollution associated with concrete. I have to make sure none of my concrete loving colleagues are on the call before I start insulting them too much. But noise is a critical one. And I guess the other thing from a life cycle cost perspective is that the vast majority of the costs are actually coming from the use phase. So they're associated with the surface characteristics of the pavement. So you've got basically higher rolling resistance with concrete, which consumes more energy to accelerate your vehicle, right? So that's kind of the big, I guess, major reason we're using, a couple of the major reasons we're using asphalt. The upfront materials costs are actually a pretty small drop in the bucket compared to the entire life cycle.
Fascinating. I'm looking forward to our discussion later today, Professor.
Definitely, me too. It'll be really exciting.
Okay, I don't see any question yet. So I have a question, Professor. So you mentioned about robust decision making in this decarbonization policy, and I'm curious because decarbonization policy and all the strategies about EVs and autonomous vehicles all have not been done in our real world, right? So how you in way you design the strategies, how you design those strategies, is there any uncertainty that you consider, like how we can produce those kind of multiple strategies and then call it robust?
The method is explicitly designed to deal with uncertainty in the performance of these vehicles or the performance of the technology. So for automation, there's some technical uncertainty about the amount of power per kilometer driven that an automated vehicle will require because of both the sensor equipment and the computing equipment. So we can get a first principles range of that, right? It's not going to be nuclear power plants worth, and we kind of have an understanding of what the hotel loads are of a normal electric vehicle, the non-motive loads from normal electric vehicle, and we can create a range of well, we think it's going to be between here and here, and that's just one element that the model is going to sample from in order to come up with a region. And so there's all of these little kind of ranges add up to a bunch of bigger ranges that now help us understand where the big uncertainties are. And it might be that if little elements of this don't affect the answer in a big way, and we can not worry about the uncertainty, or we figure out these really affect the energy in a big way, and we want to push on those to make those more efficient.
Yeah, because I was curious because you showed us like a bunch of scenarios or strategies, right? Which one is like robust, which one is like good, and which one is like the bad strategies. So yeah. So I'm looking for if we have, I believe we don't have further questions. So that's all, I think. Thank you so much for the presentation, Professor. We really enjoy it. Thank you for the time, for meetings, students that you provide. And I believe we are in the end of the meetings. Thank you, everyone.
Thank you so much. I'm very grateful. Best wishes to everyone for the rest of the semester. Happy to connect with anybody offline that wants to talk. Thank you so much, Denisa. I'm very grateful.